today we stay more technical, okay, for a while at least. So the idea is to understand better the concept of functional, because we will base our presentation of mechanics using Lagrangian ideas, and Lagrangian ideas are based on action functional. So I strongly suspect that, but I cannot prove, that mechanics was born using a sort of variational principles. This suspicion is based on the fact that the tradition is transmitting us so-called Dido's problem. Dido's problem can be formulated in modern language as follows. Given a closed curve, or better, given the set of closed curves, and assuming that the perimeter of such a closed curve is fixed. So you assume that this quantity, this is a formula which could be written only when calculus was invented, so you need derivatives. This is the derivative with respect to S. This is the well-known formula for length of a curve. Okay? So if you consider the set of closed curves having a given perimeter, the problem is to find that set of curves such that the area is maximum. The tradition talks about Dido, because the story is more or less the following. The story tells that when the first group of founders of Carthago arrived in the location of Carthago, Dido found an agreement with the local king. The king told her, you will be allowed to build your city on the area which you can enter with a piece of leather obtained by a comb. But the clever Dido was cutting in very thin stripes, and as she knew that the perimeter, given a perimeter, the curve having maximal area is a circle, using this small set of stripes she could get enough land to found Carthago. We do not know how this problem, maximization problem, was solved in Hellenistic mathematics. What is sure is that after Lagrange, this problem became easily solvable, and before Lagrange, this was a serious challenge. The technique is rather involved. Maybe I will leave it as an exercise when we'll have discussed a little bit the properties of Lagrangian functionals. Okay? But I want to talk and make you understand in greater detail what we are doing. We have a set of functions. A curve what is a curve? You block an interval, then you have a variable in this interval, and then you have two real functions of the real variable s. X of s is giving you the first coordinate, y of x is giving you the second coordinate, and when s is varying, you have a curve. Of course, in order to be allowed to calculate this integral, you need that x and y must be derivable. You need to calculate the derivatives of x and y. Okay? This integral must exist also, which is not always the case. Okay, so if you have a, say, C1 curve, so if you have, or piecewise C1 curve, then this expression for perimeter is well posed. This expression for area is, you can find more elegant vector-based expression for this, but this drawing tells you why this quantity with minus sign gives you the area of this closed curve. If you change of a small dx at a given y, you get this area. So when dx is positive, you subtract. So this is the reason of the minus. And when you have a negative dx, you have this quantity. Okay. So with this trick, easily you get in terms of course, this means dx over ds. And so you get the integral to be calculated. So in the set of C1 curves, you have the following problem. C1 couple pairs of functions. So you have the function x of s, you have the function y of s, y of a and x of a is equal to y of b, x of b, because you have a closed curve. Okay? So given this set of functions, you are able to map each of these pair of functions into a real number, the perimeter or the area. I have chosen this example because I want to give you something strongly related to geometry. We have an immediate grasp of geometry, so we understand what we are doing. Okay? So the idea is that you build with suitable operations, starting from pairs of functions, to real numbers. And your problem is, given a given constraint, you have fixed the perimeter, you want to find which curve produces the maximal area. So instead of having functions f defined in a domain D included in Rn, having value in R, you have a function, but it is clumsy to use the expression function. The function is defined in a set of functions. Okay, so the idea is to introduce another word. So you talk about functional for underlining the fact that the domain of this due function is a set of functions. So the habit is to use a distinguished word for this particular class of functions. If you are accustomed to Zermelo-Fraenkel theory of sets, everything is a function. Whenever you have a rule which maps elements of a given set into elements of another given set, you have a function. But in this circumstance, you have at the lower level real numbers. You have functions mapping real numbers in other real numbers. You are building a set of curves and you have a function defined on your set of curves. So the domain of the functional perimeter is the set of curves which are rectifiable. So for which you can give the concept of length. A particular subset of rectifiable curves is the set of C1 curves, and here we try to avoid too complicated mathematical discussions, so we limit our attention to this particular domain. So we have a big difference between functions defined in Rn or a subset of Rn and functionals. The complexity of mathematics involved is much higher when you deal with functionals. Okay? However, the clever idea, the very clever idea of Lagrange is that the concept of first variation of f, this function defined in Rn having values in R, okay, this concept can be generalized for functionals. And we have to learn how to do it. This was the beginning of modern mathematics, mechanics, okay, and in some aspects also of modern mathematics. So I want to recall, to reinterpret for you the concept of gradient of f, because we need to rephrase it in such a way that generalization will be easier. Okay? So, let us say, when you have, let us start with a function defined in R having values in R. When you have the maximum, which is the idea, how do we prove that in a point x naught where a function attains a maximum, the derivative of f is 0. If you remember, the idea is the following. I write f of x minus f of x naught plus equal f prime of x naught times x minus x naught plus infinitesimals. This is well-known Taylor's expansion. Okay? The idea behind Taylor expansion is that f of x minus f naught can be approximated by means of a linear function whose coefficient, the expression coefficients we will not be able to use anymore later, but in the case of real function of real variables, a linear function has a unique coefficient whose coefficient is the derivative of that function in the point x naught. Okay, now imagine that this coefficient is not vanishing. Say it is greater than 0. If you are close to x naught, then this infinitesimal can be neglected. If you consider x greater than x naught, this quantity has to be positive. But if x is smaller than x naught, then this quantity is negative. So x naught, the poor x naught, cannot be a local maximum or a local minimum. So this is taught, or at least it was taught, in every final class of scientific high school in Italy. Then f prime has to be 0. Now, in the epoch of Lagrange, this was advanced mathematics. This was at the borderline, at the boundary of knowledge. Okay? Lagrange decided to generalize this approach to the problem of searching maxima and minima to n variables functions and to functionals. So we try to follow his steps. So just for trying to do the work easier, we start with the case of n variables, and then we attack the problem of functionals. Now f of x, now x belongs to Rn. I will use the vector space structure of Rn. So I will use the fact that you can calculate the difference between 2 points in Rn, okay, and that with n vectors independent, one of the others, you can represent by means of a linear combination all vectors in Rn. So we will exploit the trivial fact that Rn is an n-dimensional vector space. However, this is not essential in our reasoning. What is essential is that it is a vector space. This is what is important. So we will be able to generalize our reasoning when the domain is not anymore a finite dimensional vector space. Okay? So f of x minus f of x naught equal. So we have to define the differential, or the first variation of a function defined in Rn having value in R. So we say that a function f, definition, a function f is differentiable in x naught if and only if there exists a linear function L0 such that this linear function applied to the increment x minus x naught plus infinitesimals of higher order verify this equality. In formal words, limit for x tending to to x naught. Of course, this limit has to be intended in the sense of Rn. Okay, so analysis second year, you should have learned which are the spheres in Rn and in which sense this limit has to be intended. So what you have? You have that fx minus fx0 minus L naught x minus x naught absolute value divided the norm of x minus x naught. This is equal to 0, which is equivalent to say that this is an infinitesimal of higher order than x minus x naught. Okay? So this, which seems to be a rather abstract definition, actually is a very powerful tool of calculation, as we will see. So I try to generalize the concept of derivative. I am not able to write f of x minus f of x naught divided x minus x naught. Why I cannot do this? These are two real numbers. These are elements of Rn. So there is no meaning of this operation. So the crucial idea is the following. I look for a linear function which is mapping vectors in Rn into real numbers. Okay. And this linear function has to produce the best approximation of the increment in the set of linear functions. So, in a sense, I am looking for that linear function such that, in principle, there could be many of these. Actually, there are strange functions for which you must define sub-differentials. But, I mean, we don't want to talk about this. If f is regular enough, then there is only one of these functions L naught. So, among linear functions, I want to find the one which gives me this formula, which verifies this formula. This linear function is the best available linear function for approximating the increment of the function f. Okay? What is astonishing is that you can prove a theorem. If L naught exists, then all partial derivatives of f exist, and when you build grad f in this way, df over dx1, df over dx2, df over dxn. So if you introduce the vector gradient of f, you calculate this gradient in x naught, you place this gradient here. This application now is meant as the inner product between grad f and x minus x naught. Never forget that x is made of x1, x2, xn, and x0 is x01, x02, x0n. Okay? So, when you calculate grad f inner product x minus x naught, you get a number. This number gives you the best linear approximation of this increment. The inverse of this theorem is rather a little bit more complicated. If you can calculate all partial derivatives, and if these derivatives are all continuous in the neighborhood of x naught, then this formula is true. So if you know that this formula is true, you are assured that there are all partial derivatives. The vice versa is not true. You may be able to calculate all partial derivatives without being assured that this formula is true. In order to be assured that this formula is true, you need to know that these partial derivatives are also continuous in the neighborhood of x naught. This is a very important characterization of differentiable functions. Okay? Now, of course, we could open, but we will refrain from this. We could open a parenthesis. We could start talking about linear functions. So we could develop the theory of linear functions defined in a vector space having values in another vector space. Okay? This theory is the basis of analytical geometry. One of the main theorems in this context is Rouchet-Capelli theorem. Linear systems are studied with this theory. If needed, we will try to focus on some of these subjects, but I hope you master this subject well enough. Okay. So, even if for a function defined in Rn having values in R, the incremental ratio doesn't mean anything anymore, we still are able to define the derivative of f. Now, the derivative of f is a linear function. Of course, when you change x naught, you change the linear function. With different points x naught, you get, in general, different linear functions. Okay? Very often, we call L naught as the tangent function to f. Okay? Well, now we are ready to attack the problem solved by Lagrange when he was 16 years old. We are talking something which happened in 18th century, so it's something very old. First of all, Lagrange understood that he couldn't study every functional, which is very clever. When you try to do the theory of everything, you are lost. So he decided to focus on a particular class of functionals, which we will call Lagrangian functionals. Why he wanted to study this? We will see in one of the coming lectures that before Lagrange, Euler wanted to study the equilibrium and the dynamics of beams. And in order to find the evolution equations of a beam, he introduced an energy, a deformation energy, and he looked for the minimum of total energy of a given beam. So his idea was the equilibrium shape of a beam is that shape in which total energy attains a minimum. This was clear in his idea, in his mind, and he could write the energy functional to be minimized. But he could not, for more than 10 years, find the minima. You can imagine how he was upset when a young student of high school sent him a letter in which that problem was solved. By the way, Lagrange was very clever. He didn't send a letter to Euler without having, how to say, found some safe counter actions ready in case Euler would have tried to steal his idea. Actually, he had published in French the solution in a journal he was founding for this purpose. And it is told that he wrote all the other papers in the journal for quickly producing the first issue. Many of the authors of these papers became full professor with these papers. By the way, he became full professor being 19 years old. Okay? We have to understand the idea of Lagrange function. So, consider Q1, Qn, n real parameters. Consider a function, a set of functions, S, Qi of S, where I belongs to 1 up to n. So you have n real variable functions. Okay? S belongs to an interval. Qi of S belongs to real numbers. So you have n real valued functions. In the previous example we treated perimeter and area. I was 1 or 2. We had x and y of S. Here instead we have n of these functions. By tradition, Q1, Qn are called Lagrangian parameters. When needed, I will call with Q of S the set of all these n functions. You can estimate the derivative of each of these functions, and you can consider Q dot of S the vector of Lagrangian derivatives. Okay? Then be attentive. This is a deep, clever trick. You consider a function L, Lagrangian, defined in Rn, Cartesian Rn, Cartesian R, with values in R. So the Lagrangian has the first variable belonging to Rn, the second variable belonging to Rn, the last variable belonging to R. Okay? So this is a function of, we can call it Q, Q dot, and S. Q is nothing, is an element of Rn. Q dot is nothing else than a variable in the second copy of Rn, and S is an element of R. So up to now you have a function of 2n plus 1 variables. You are grouping the first n, the second n, and you are leaving alone the last one. Okay? So instead of considering the most general functional, the clever Lagrange decided to introduce this family of functionals, which we can call Lagrangian functionals. So I call Q bracket dot bracket here. I introduce this symbol because I want to remind you that the functional we are introducing is defined in the set of in this set of functions. So the domain is not Rn. The domain is the set of functions. Okay? We can call C1 functions. We can consider one-time differentiable functions defined in this way. Okay? So we introduce this integral between, we have A and B, between A and B of what? L Q of T, Q dot of T, T dt. So what we are doing? We are considering one given function. We are calculating the image of this function. We get n real numbers. Then we calculate the derivative of these n functions. We get n more real numbers. The Lagrangian velocities of the given function. And we replace these velocities in the second set of n variables. Then we plug in the variable t and the last place. What we get is a number. Okay? When you vary t, you get a varying number. So here you have built a real valued function of one real variable. You can integrate it. What you get at the end? A number. So this is a particular class of functionals. Think about the two examples I gave you. They belong to this class. Consider that the value of the Lagrangian estimated at instant t depends on the value of q at instant t and on the value of q dot at the same instant t. In this sense, this functional is local. Okay? What is doing q of I in another instant or in another value s is not influencing the value of L estimated in the variable t. Okay? So this is a peculiarity of Lagrangian functional. Now this tool is very powerful because every known, maybe every is a big word, the great majority of known finite dimensional models for physical phenomena are minimizing a functional having this form. So I am partially fulfilling my promise, that is to teach you to formulate the evolution equation of everything. Okay, I can tell you that this gives you a very powerful tool for finding the evolution equation of the great majority of finite dimensional systems. Okay. Actually, every computer is using a finite dimensional approximation of the eventually infinite dimensional model for you are dealing with. So in a sense, this is a very powerful tool. Okay. Now, following D'Alembert and Lagrange, we say that the evolution of this very general system is minimizing this functional. Of course, I'm forcing the mathematics by giving you this interpretation. We could be talking about, I don't know, a shape, everything which can be modeled with a set of n functions. Okay? If we have a set of n functions which minimize a functional of this shape, then the reasonings which I'm going to show you apply. Okay? So now the idea is that we want to find the first variation of this functional. So in a sense, which has to be made clear, I have Q of t, which is the candidate to be a minimum or a maximum of your function. So I call it Q star. And then I vary this Q star a little bit. So I have Q star of t plus delta of Q of t. Okay, now I don't want to rush. I prefer to tell you less things but more clearly than filling your head of things in a rough way. Of course, what means small? We need an estimate of being small. In Rn, we introduced norm of x minus x naught. Okay? To understand rigorously what we mean with small in this context, you have to wait more than 100 years after Lagrange. Fréchet introduced the right concept of being small in this context. So in my opinion, this theory is very useful, also because it is teaching you to focus on exactly the important things in one theory. You have to be ready to neglect problems you cannot solve precisely and you will solve later, because you have to learn a tool for solving a problem. Okay. So the right measure of rigor is also taught by this Lagrangian theory. Okay. So in a sense which we will make clear while doing the calculations, this delta Q is small. This is the beginning of a theory which is called now functional analysis. Functional analysis is introducing topologies in the set of functions. So it is telling you what means that two functions are close, in a sense. How to calculate limits, how to define continuous functions, continuous functionals, when the set of the domain where this function is defined is a set of functions. This is a very delicate mathematical problem. We solve it following the clever intuition of Lagrange. Which is the clever intuition of Lagrange? Delta A, the variation of action, it is equal to the first variation of action which is a linear function of delta Q plus infinitesimals of higher order. Of course, we have to understand what is a linear functional defined in the set of first variations of the set of Q's. Okay? So, up to now, this is a very formal expression. Delta A means A of Q plus delta Q minus A of Q. Of course, we have decided to call it Q star, so delta A is equal to okay? So this is the finite difference, in a sense. Okay? The finite increment. We want to find, so you have to understand the parallel we are trying to establish. We have to find that linear functional defined on the set of delta Q's such that this finite increment is equal to the value of this linear functional on the variation of the independent variable plus infinitesimal of higher order. Of course, for telling what we mean with infinitesimal of higher orders, we need to introduce a norm in the set of delta Q's. Just for giving you an idea of what we are talking about, I tell you that this is what is done in Banach space. Okay? So, how to give a norm to a set of vectors which are functions, so in an infinite dimensional set of functions which form a vector space, it is what is called to introduce a Banach space. But Banach is much more recent than Lagrange. You will see how clever was Lagrange in avoiding all these technical problems. He writes down this finite variation, writing the integrals. So we see what he's doing. So we write integral between A and B of the Lagrangian, I have to estimate this Lagrangian in Q star plus delta Q star. I don't write t, but it means a function of t. Q star plus delta Q star dot the derivative of this t. Then I should write minus integral of the same thing in Q star. The integral of the difference is the difference of integrals. So I jump and I write directly this. This integral is in dt. Now, the clever idea and the reason for which Lagrange is studying only this class of functionals. The Lagrangian is a function of Rn, Cartesian Rn, Cartesian R. So, as a function of Rn, a Taylor expansion can be written. So, this increment can be expressed in terms of the partial derivatives of f with respect its arguments, its independent variables. So this is the clever move which the poor Euler couldn't imagine. So you write dl over dq. Of course, when you estimate a derivative of a function of q dot and t, you calculate the derivative with respect to q, you get a function of q dot and t. You have to estimate this partial derivative. You estimate it in q star, q dot star, and t. Okay, I write it qi, and of course I need delta qi, and of course I'm summing over I. Okay? But L is not varying only because Q's are varying. It is varying also because Q dots are varying. So I add plus sum over I. Of course, the poor Lagrange was not handling summation symbol. So he wrote all this with a symbology which is very difficult to read now. Okay, these symbols were introduced by Levi-Civita much later, which allows us to write this in a much more simpler way. Okay. So we write dl over dq dot I. Of course, I call star here simply for meaning that you estimate this partial derivative in q star q dot star t. And here what you have? You have delta q dot I. The last variable is not variant. So you have no partial derivative to estimate. Of course, here you have plus an infinitesimal. Okay? One of the theorems of Lagrange about integrals we can formulate in this way: the integral of something small is small. Okay? So, if you neglect this, you replace to the finite increment the candidate first increment or linear increment. Okay? So, delta action is equal to this, and you forget this increment. In every book of analytical mechanics, when you arrive here, somebody writes, attention now, you cannot vary delta qi without varying its derivative. These two increments are not independent for functions. Okay? Up to now, remember this when you apply this theory. Up to now, you have treated delta q and delta q dot as independent quantities. If you have two dependent quantities and you write approximation formulas, you can treat them as independent. You get good results. But remember that we need to know such q star which verify the condition that the first variation of action is 0 for every variation delta q of the function. So you are allowed to change the function, not independently the value of the function and of its derivative. Okay? So now you have to write an integration by part formula to get an expression in which delta qi appears alone. So we write this in another formula, and then we add to what we are writing now. So, dl over dq dot delta q dot. I forget to write summation. I will perform linear operations, so everything is good. This is equal to d over dt of dl over dq dot delta q bracket minus d over dt of dl dq dot everything times delta q. This is a trivial application of Leibniz formula for derivation. Okay? You could also write using Einstein convention this way. Derivative is linear, so and the dot here is commuting with the delta. This is a very delicate issue. So what do you mean? So I stop here for a moment for telling you this detail. If when you talk about delta q, you are not controlling its time derivative, when you claim it is small. So if for you delta Q small doesn't mean that its first time derivative is small, you are in troubles. Because when you are inverting dot with delta, you are meaning that delta Q dot is small. Delta Q dot has to be small, otherwise Taylor's expansion you cannot write there. So the classical example which electronic engineers like very much is the following. These two functions are close both with their value and their derivatives. Instead, this function has close values to the two I was considering before, but its derivative is not at all close to the derivative of the other two. So when applying this argument, I need to be careful. My field Qi of t has to be close, delta Qi has to be small, but also delta Q dot I has to be small. So the domain of this set of functions must be a domain in which you can control the value of the functions and the values of the derivatives of these functions. So you need, if you ever heard this word, you need a Sobolev space H1. It is a space in which you can estimate the value of the function, the value of the derivatives of the function. Of course, Lagrange did not know this technical detail, but he knew that in order to continue his argument, he needed to be sure to commute the dot with the delta. And he wrote 5 pages for repeating this point. Okay? So he was aware of the fact that this was a crucial point. So here, instead of this equation, you can write the difference of these two equations. The difference of these two quantities. So here you write d over dt of dl dq dot delta q minus d over dt dl of delta q dot delta q. And you have the integral over dt. Okay? Now, the integral of a derivative is the value of the function to be derived in B minus its value in A. Of course, if this function is differentiable, if you have all regularity conditions. So, In conclusion, we have this formula and we have to discuss it carefully. Now, look at this animal. This is a linear functional in terms of delta Qi. It is another thing which was taught in last year of high school, scientific high school. This is a linear function of delta H. So here you have n independent variations, n independent delta Qi's. Okay? Here you have the value of delta Qi on the boundaries of your interval. This also is a linear functional of delta Qi. So you are very close to the aim we had in mind. Because with this formula we can estimate the first variation of action functional when you start from star function, q star of t, and when you vary this function of the quantity, of course I need another bracket there, of the quantity delta Qi. So this animal is a coefficient which multiplied delta Qi, you calculate the integral, gives you a particular functional, a linear functional, a tangent functional to the previous one. So when you know that delta Qi and delta Qi dot are small, the finite variation of A you can replace with infinitesimal variation. So the idea is exactly the same as in Taylor expansion truncated at the first order. Delta A is equal the first variation of A plus infinitesimals of higher order. What are we doing with this? You need a theorem. Do you know which was the person proving this theorem? Lagrange. Given a function f such that for every continuous function delta h, the integral between a and b of f times delta h is equal to 0, then f is 0. This is something which is taught in every class of calculus. It is very important for many reasons, but in this context, this theorem is fundamental. Indeed, it is called the fundamental theorem of calculus of variations. This theory is called calculus of variations. The generalization two functionals of standard calculations of differentials is called calculus of variations. The idea of Lagrange is very simple. If I have a function like this, okay, and if I multiply this function times another function, or if I multiply this function for every other continuous function, how it is possible I can get something different from 0, or how it is possible that I get always 0. So the idea is the following. Imagine that f continuous 1, continuous function, has a positive value in a given point x0. So f has to do something like that in the neighborhood of x0. Because it is continuous, it cannot go too far from the value fx0. Okay? So in the argument it is crucial that the function f is continuous. What this function is doing far from x0 is not important. Why? Because Lagrange is building a function which is 0 everywhere, different from 0 here, 0 there, outside. So it is sampling the neighborhood of x0. So if f were different from 0, being continuous, then one could find a delta h such that the integral of the product of the two is greater than 0. Okay? If you assume that this is equal to 0 for every delta h continuous, and if you assume that f is continuous, then the only possibility you have is that f itself is vanishing. In modern words, very elegant, some electronic engineer will tell you that he knows, simply because he learned it by heart. The inner product of a continuous function with another continuous function for every other continuous function can be 0 if and only if f is 0 itself. So in the theory of Hilbert spaces, this is trivially stated. Okay? But again, Lagrange did not know Hilbert spaces. He considered a function f continuous 1, and assuming that this f were different from 0 in one point, he proved that you can find a delta h such that this integral is greater or smaller than 0. So the only possibility to have this integral 0 for every delta h for a given f is that this f is vanishing. We are using a sampling function inside the interval a, b. Okay? So, we have proven the celebrated Euler-Lagrange equation. This is called Euler-Lagrange simply for political reasons. Lagrange found it, but Euler was telling it is good. it is right. So, you need to be certified by somebody, and only for this reason the equation is named also after Euler. Okay? We will see that this is giving to you the evolution equation of a great class of finite dimensional models. But, or also equilibrium conditions for beam. We have to manipulate it a little bit, but you get it also. You can use it for minimizing every functional. So not only action functional, you can also minimize energy functional and find the minima of energy. Okay? What is happening to the boundaries? You have two possibilities. And this is the first occurrence of famous duality. Either in boundary conditions, either you assume that delta qi is 0. So you limit yourself to a set of functions q star having given values in A and B. So you can say, I'm looking for the minimum of my action in the set of functions where q of A is given and where q of B is given. You block the value of QA, QB. Then delta QI admissible is 0. So this animal disappears by itself. So your equation has this shape, and the boundary conditions are QA given, QB given. So you have to find among the solutions of these differential equations those functions which have a given value in A and a given value in B. Okay? This is when you give boundary conditions. You could decide, for instance, that you are looking for the solutions of your problem with Q of B free. You could decide that delta QH is arbitrary. Then your first variation has this animal. And this animal has to be vanishing for the usual reasoning. So when you have arbitrary delta QH, the dual condition dl over dq dot h calculated in B equals 0 must be verified. The wonderful peculiarity of this reasoning is the following. You always get exactly the correct number of boundary conditions which you need. The problem you get if the Lagrangian function is well behaving, the problem which you get is always well posed. Okay, now you could consider all this treatment rather mathematically abstract. Okay, I don't know if you know it, but I hope you know it. This was taught to every engineering student in the last 150 years, and only very recent and disgraceful changes in the order of studies have cancelled this stuff in the curriculum of every engineer. I believe that nobody can understand any numerical code if he doesn't understand this structure. You know, you heard about Lagrangian points, Lagrangian parameters. Okay. They come from this equation. If you have a finite dimensional system, 99.9 chances is that this finite dimensional system can be put in this form, the evolution equations or the equilibrium equations. Okay, but I want to discuss with you, before ending this discussion today, I want to try to let you understand a little bit in more detail what we evocated in the first lecture. The action functional has to be postulated for a given system. Okay, so the first postulation move is the following: L. So one has to start his investigation conjecturing the structure of this Lagrangian. This is a conjecture. Do you remember, we have in the world of ideas, we have mathematical objects. So the kinematics first means I choose the n Lagrangian parameters. I have to choose them in the most appropriate way. Next step is I choose a Lagrangian. Okay? Then I find the Euler-Lagrange equations. Then I consider how this system is interacting at the boundaries or at the initial time, which are the initial boundary conditions. Okay? Then these equations tell me the evolution of the system or the shape of the equilibrium configuration of my system. Once I have solved these differential equations, I have a way for forecasting the behavior of the system I'm studying. Only then my conjecture can be tested with experiments. If my Lagrangian is good, if my initial or boundary conditions are good, then I get the correct forecasting for my system. And I can claim that my modeling is correct. Okay, now, this is very nice, this is very useful, but it is not enough. This is the bad news. This set is a set of ordinary differential equations. Okay? Everybody, I hope, among you has seen this problem. I have a beam, an Euler beam, which is moving under load. The configuration of this system is given in terms of u of x and t. X is the abscissa in the reference configuration of the beam, and u is the transversal displacement of the beam. T is time. As I started to tell you, this space of configurations is not finite dimensional. So the theory I developed for you up to now cannot be applied. Okay, this was clear to Poisson, to Cauchy, to Navier, to Lagrange. It is a typical way of reasoning of human beings. When you cannot solve a problem, then you claim it is useless. It's a typical attitude of human beings. Which is the reasoning of Poisson? There are no infinite dimensional systems in reality. We are tired. You had enough technical details for today, but I want to tell you how you have to be careful in handling the so-called wise reasonings of many practical people. Okay? In this period, I'm starting to believe that one of the biggest tragedies of the mechanics of 19th century was the existence of Poisson. Not only because he was against Viola, but because he was very stubborn and biased. So the reasoning of Poisson is the following. Matter is made of molecules. In the universe, there is a finite number of molecules. Therefore, these are the equations of the universe. You have to study nothing else than this. You don't need to deduce the Euler-Lagrange equations for infinite dimensional systems. There is a big problem in this. Do you know how big is Avogadro number? And do you know how many moles of molecules are existing in the universe? So it is not conceivable even to study the deformation of a beam using these equations. So the big problem we are facing now is not to accept a metaphysical vision of the world, where molecules are the last elements of matter. Then you discover that you have atoms, then you find always smaller components of matter, but this is another story. Assume that you can say that we stop somewhere. We stop at a given level. Then we have a finite number of particles. By the way, do you know that Archimedes was calculating in a famous paper the number of grains which you can place in a sphere whose radius is the radius between Earth and Sun? I mean, the idea that the universe is made of many molecules and the effort of finding this big number is very old. Okay? Laplace had a delirium of omnipotence. When he wrote these equations, he applied these equations for the motion of planets. He met Napoleon III and he said, these are the equations of everything. Napoleon III asked him, but Professor, where is God in your theory? And he answered, this is an hypothesis of which I have no need. These equations are telling me everything. So, metaphysical attitude is very dangerous. What do you want to study? A beam? Find the action which is more suitable for studying a beam. Okay? If you want to study the evolution of an economical system, find the Lagrangian which is describing the evolution of an economical system. I will show you shortly that this is possible. Okay? Every phenomenon you attack with a given Lagrangian. Okay. Sometimes instead of following every molecule of a mechanical system, it is more convenient to group these molecules in what we call material particles. Many. Say an Avogadro number of molecules. Instead of getting ordinary differential equations, but many of them, you will get fewer partial differential equations. Partial differential equations are bad. You cannot solve them easily. But if you have few of them, you may have a chance to solve them in a way. Okay? Now, and then I stop. What is interesting is the following. You write, say, Laplace equations with suitable boundary conditions in a domain. Okay? And you have no idea, except if this boundary, this volume is well behaving. This is a typical problem in electrostatics. I hope you have seen it once in your life. Okay. Do you know what people in numerical analysis are doing? Introducing a Lagrange, finite dimensional. They find a step function phi n, which is approximating phi, and they formulate this problem in a variational way, and they find Euler-Lagrange equations for this approximating function. But they are not following the molecules of a luminifer ether or something like that. They introduce the field phi. Then they find a finite dimensional approximation of this field, and then they find the Euler-Lagrange equations for this approximate finite dimensional model for your electrostatic field. So that devil of Lagrange gave us a tool which is very powerful, even with computers. Okay? So we will try to understand this better and better. Okay?